Engineering. It's a vague word that people use a lot. If you're watching this video, take a good look at the device you're watching on. It could be a laptop, a phone, or a tablet. But have you ever wondered how exactly are these things achieving all these tasks? How could an ordered mass of metal and glass be able to provide service that improves your quality of living? 50 years ago, all these things we take for granted were still science fiction. Welcome to the very first episode of the Engineer's Transits, where we will tackle a lot of engineering topics, something about math, and also the sciences. There will be a lot of topics in the future, so stay tuned. And also, if you want some discussions, some suggestions of other future topics, please don't hesitate to comment down below in the comment section, like, and subscribe. Now let's get to it. Civil engineering works more in a bigger scale, and without it, the group of nomads wandering around the Fertile Crescent never would have settled and led to the creation of society we have today. Modern civil engineering is made out of more focused subdisciplines, each one no more important than the other when it comes to building societies in our modern world. The first is construction. Construction is about carrying out the plans and executions. A construction engineer's job is to maintain a high level of standard of safety in the sites. Construction is usually at the end of the engineering process, where all of the concepts and plans will now be executed. Construction is especially important because it is present in almost all civil engineering subdisciplines, and it's what makes civil engineering a very tangible science. If construction is the body, structural engineering is the skeleton. Structural engineering's main purpose is safety and economy. A structural engineer's job is to properly simulate all the loading conditions and make sure all design and components are up to code at the same time and find a way to make the different structural members less costly as possible. Design considerations will include strength, stiffness, stability of the structure, and earthquake loads. Earthquake engineering is also part of this category, as structural engineers must find a way to incorporate earthquake loads in design and make sure that the structure can withstand the worst. Environmental engineering, sometimes also known as sanitary engineering, is probably one of the most underappreciated civil engineering subdiscipline. Environmental engineers typically handles the treating of chemical, biological, or thermal wastes, purification of water and air, and also the remediation or rehabilitation of contaminated sites. Environmental engineers are usually the ones sought out to give an opinion on the environmental impacts of a project or sites. Water resource engineering deals with the collection and management of water from a natural resource. This subdiscipline oversees the prediction and management of the quality and the quantity of water in underground aquifers and natural reservoirs. Hydraulic engineering also falls into this category, where designs and maintenance of the pipelines and water supply networks are handled. Water resource and hydraulic engineering mainly employs the concept of fluid pressure, fluid statics, fluid dynamics, and hydraulics. Transportation engineering is mainly concerned with moving people around and goods from point A to point B as efficiently as possible. Transportation engineering involves planning, designing, constructing, and maintaining transportation infrastructures like roads, canals, highways, railway systems, ports and airports, and mass transits. Geotechnical engineering focuses on studying rock and soil support in civil engineering systems. Geotechnical engineering mainly applies the principles of soil mechanics and fluid mechanics in this subdiscipline. Before going forward with any civil engineering design, a geotechnical engineer will need to inspect and conduct tests to find out what kind of soil lies underneath the future structure. Such data will be crucial in the structural design of the building, as it will determine the overall stability of the foundation of the structure. Other areas of civil engineering include urban planning, where municipal design and planning is carried out, surveying, in which civil engineers measures dimensions that are on or near the surface of the earth, and material science engineering. Although this one is more of a generalized and is applicable to other engineering disciplines as well, material science and engineering studies the fundamentals of materials and their properties. Electrical engineering is a relatively more recent type of engineering focused in the design, application, and uses of electricity, electronics, and electromagnetism. Although the interest in the study of electricity as a science went as far back as the 17th century, in the 19th century, intensified research on the subject after the popularization of the electric power generation, telegraphs, and telephones. Visionaries like Nikola Tesla paved the way for alternating currents, for ever-changing power distribution in a massive scale over huge distances. Galileo Ferraris, with the electrical theory and the induction motor, to Oliver Heaviside and his theoretical models for electrical circuits. The 20th century gave rise to advances in electromagnetism, radio waves, and wireless communication. Such advances in electronics technology also gave birth to the world's first fully functional, electronic, and digital programmable computer, the ENIAC, or the Electronic Numerical Integrator in Computer. Electrical and electronics engineers work in a wide range of industries that may vary tremendously depending on the type of job. Although sometimes used interchangeably by lay people, electronic is different from electric. The main difference is that electric circuits have no logic or decision-making capabilities and can only supply and regulate power while electronic circuits can. Power engineering deals with the power generation, transmission, and distribution of electricity. This subfield also covers the design on the devices such as transformers, generators, motors, and power electronics. The power grid is the electrical network that governments utilize to distribute large quantities of power over cities and territories. Electronics deals with the design and testing of electronic circuits that utilize the components such as capacitors, resistors, or transistors in order to assign a specific functionality to a device. Electronics obviously has a very broad scope of applications from radio technology to computers and microprocessors. There's a lot. Integrated circuits were also invented in the 1959 that paved the way to manufacturing smaller and denser circuits that did away the bulky and often power-hungry components of before. This sparked the race to develop an even smaller and more powerful computer, which leads us to continuing further the technology of integrated circuits and microfabrication. Microelectronics can be created at a microscopic level. Going further, nanoelectronics further scales down this engineering feats, in which devices have approached the nanometer realm, with below 100 nanometer processing becoming a standard since 2002, and it's become even smaller since. Microprocessor and nano devices are already at use today in powerful computing units and devices. Mechanical engineering is one of the oldest branches of engineering, with a focus on designing, analyzing, manufacturing, and maintaining mechanical systems. Find any device or system that moves, a mechanical engineer probably designed it. As early as 5000 BC, one of the simplest machines in the form of a simple wheel, an axle, was invented in Mesopotamia or modern-day Iraq, and transformed how people transport large objects without utilizing animal assistance. This is the basic function of mechanical engineering: how to use mechanical systems or machines to assist you and improve human quality of life. Mechanical engineering became widespread, most notably in the 18th century when the Industrial Revolution happened. It was this time when manufacturing and industry became widely practiced. It drove economies around the world forward and further improving the quality of living of millions of people. During the 19th century, more advancements in physics led to the development of mechanical engineering science. Mechanical engineering employs heavily the principles of physics, mainly mechanics, thermodynamics, fluid mechanics, and material science. For example, if the project involves designing a vehicle, statics, the physics of stability in non-moving bodies, may be employed to design the frame of the vehicle, pinpoint points of stress, in the body and how to increase safety, while dynamics may be used in designing the car's engine to evaluate the forces in the pistons, as well as engine cycles, and mechanics and materials also might be used to choose the right materials to use for the frame and the engine to make it lighter, more cost efficient, of course, even better if it's maximized. Meanwhile, fluid mechanics is mainly used to design ventilation systems for the vehicle and the design intake system for the engine. Mechatronics and robotics is a subdiscipline of mechanical engineering. It's a combination of mechanics and electronics, to be honest. It is an interdisciplinary branch of mechanical engineering, which means that it involves other engineering sciences, in this case, electrical engineering, as well as software engineering that is concerned with integrating electrical and mechanical engineering to create hybrid systems. When people hear about mechatronics and robotics, they usually imagine grand feats of robotics involving super intelligent mechanical humanoids performing complex tasks. But actually, one of the most notable and common example of mechatronic system is a CD-ROM drive. A CD-ROM drive is made out of a mechanical system that opens and closes the drive, spins the CD, moves the laser, while an optical system scans and reads the data on disk, and converts it to bits. Then, an integrated software communicates the contents of the CD to the computer. Such a mundane and everyday object people take for granted is actually a well-designed mechatronics system, most probably designed by a team of engineers. Similar to civil engineering, structural analysis is also a branch of mechanical engineering dedicated to examining how and why objects fail and how to fix problems and improve performance. Similar to civil engineering's structural analysis, mechanical engineering's version focuses on the analysis of failures. Just like a civil engineer would, a mechanical engineer would design with failure in mind to make sure it won't. Mechanical engineers also dabble in the field of thermoscience, where engineering thermodynamics is utilized to design engines, power plants, heating, ventilation, air conditioning, insulation, and others. If civil engineering is more concerned about static objects and structures, mechanical engineering dabbles more in dynamic systems or moving objects. Chemical engineering is the application of chemical, physical, and biological science to the process of converting raw materials into more useful and valuable forms. The work of chemical engineers is very broad, ranging from nanotechnology to large-scale industrial processes. Chemical engineers are involved in many aspects of plant design and operations, process design, control engineering, chemical reaction engineering, nuclear engineering, and biological engineering. Chemical engineering, as a discipline, is relatively new, as it was first taught in London in 1887 by Henry Edward Armstrong. A year later, Lewis M. Norton taught the first chemical engineering course at MIT, or the Massachusetts Institute of Technology. At the time, the Industrial Revolution was shifting into high gear, and the demand for unit operations, a fundamental concept of chemical engineering, was increasing. During this period, it was difficult convincing other engineering peers that chemical engineers are engineers and not chemists. The main difference between a chemist and a chemical engineer has to do with their originality and scale. Chemists are more likely to develop a new and innovative material, and chemical engineers are more likely to develop the processes to take these new materials and produce it at a large scale for industry applications. Everything that has something to do with the production of chemicals, materials, and consumption is handled by the chemical engineer. The industry roles of a chemical engineer are very broad, that one video will not be able to cover it all. Ranging from biomedical engineer or biochemical engineering to reactor technology for power to something that people take for granted like food engineering. Chemical engineering has grown quite the collection of subdisciplines under its name. Engineering is never a singular discipline. More often, projects usually involve a team of different engineers working together. For example, with buildings or building construction, it's not just about the civil engineer actually who designed the structure and oversees the construction. A building needs power and circuitry and also ventilation and air conditioning. Therefore, in pre and post planning, an electrical engineer and mechanical engineer will have to design their corresponding plans parallel to the architectural and structural aspects of the project. Other branches of engineering include aerospace engineering is closely related to mechanical engineering and is more specialized and specific to the design of aircrafts, satellites, rockets, helicopters, and so on. This branch studies the pressure differences in aerodynamics to safely design and ensure the efficiency of the aircrafts that we're going to fly. Next is marine engineering. Marine engineering is associated with anything on or near the ocean. Examples are, but not limited to, ships, submarines, oil rigs, structures, watercraft propulsion, onboard design and development, plants, harbors, and so on. There's a lot of them. It requires a combined knowledge in mechanical engineering, electrical engineering, civil engineering, and some programming abilities. So marine engineering is actually more interdisciplinary than anything else. Next is computer engineering, one of the most common ones nowadays. Computer engineering is a branch of engineering that integrates several fields of computer science and electronics engineering, required to develop computer hardware and software. Computer engineers usually have training in electronics engineering or sometimes electrical engineering, software design, and hardware-software integration instead of only software engineering or electronic engineering. So there's a lot. With computer engineering is one of the more growing types of engineering nowadays because the technology we're using for computing technology has been evolving ever since. And in every 10 years, there's always a new technology that's going to revolutionize the industry. Obviously, with engineering, there's a lot more where this came from. There's a lot of engineering principles and disciplines out there. So the list that's in this video does not represent all of them, but rather they form the foundation that applies to most, if not all, of engineering jobs or engineering disciplines. Thank you for spending time on the very first episode of the Engineers Transit. Please comment down below on what you think of the video, or if you have any other suggestions for future topics. Please like, comment, and subscribe, and we will see you in the next video.